Okay, so for this shaft design, what we should focus on it? So we should focus on the shaft design for stress, of course, and the failure criteria for shaft, and the shaft stress analysis. Okay, and how to define the fatigue factor of safety for shaft. And the purpose of the shaft design is to design its diameter. Okay, design. So I mean, what's the diameter of the shaft? Will be the optimized under specific fatigue loading. Okay. Okay, and then there's examples here. Okay, so suppose we have the a shaft with bearing A fixed on the bearing A and the bearing D right here, and this shaft is transmitted by gears. Okay, by gears, and this gears or this is called the pinion. Okay, so for the larger gears, it's called the gears. Okay, and the smaller one is called the pinion. Okay, the pinion. So if we plot its free body diagram, okay, it's free body diagram right here. Okay, basically the part of this AB without torque applied to it. Okay, so there's a bearing at this end A and B. Okay, and there's no torque applied within AB and CD also. Okay, therefore, we can say the critical fatigue occurred at the shaft BC. Okay, let's see the main portion of the shaft subjecting to the fatigue or the torque. Okay, so it's a critical location candidates for torque. Okay, therefore, for this BC shaft, the torque equals to the F1 times R1 or F2 times R2. And this torque is a constant. Okay, and where the F1 is the tangent force. Okay, it's the tangent force. It's the tangent force comes from the gears. Okay, there's a reaction force from the gears. Okay, so there are two gears and two gears contact with each other. Hold on. Contact with each other, and there's a reaction force. Okay, there's a reaction force. It's defined as the F1. Similarly, there's a two gears contact with each other, and there's a reaction force. It's called the F2 right here. Okay. Okay, so for this, that's what I mentioned previously, for this AB without torque applied, right? And this actual loads produce small constant stresses. Therefore, this actual load can be negligible. Okay, therefore we don't have to consider the actual loading applied to this shaft. Okay, to this whole shaft. Okay. Okay, is that clear? So for this free body diagram, we can plot its shear and bending moment diagram. Okay, we can plot the shear bending moment diagram, right? So at this end A, this actual loading can be ignored, and there's only the reaction force. Similarly, the actual loading at this point D can be ignored. Okay, can be ignored. We can define the moment, the resultant moment at point B and C. Okay, B and C. Okay, therefore the moment, the resultant moment at point B equals to the square of root, right? mz1 q plus the my1. Sorry, mz1 square plus the my1 square. Okay, the square root of that. You know what I'm saying? So if you look at this coordinates x direction y and z, therefore the mz1, okay, means the force, the tangential force, produce the bending moment in z direction. Therefore, for this z direction right here, right? So there's a bending moment, mz1. Okay. Similarly, at point C, similar at the my1 here, which means we have this coordinate in y direction, and the moment produced from this tangential force defines the my1. Okay. Therefore, there's a resultant moment. Okay, resultant moment resultant moment. Okay, MB. Okay, so similarly, we have this MZ2 and MY2 right here. So this MZ2, the moment in Z direction, comes from the tangential force F2, right? So for this Z direction right here, and this moment MZ2. Similarly, in Y direction, we have the moment. It's the MY2. Okay, MY2. And then we can figure out as say the resultant moment. Resultant moment, MC. MC. Okay. Resultant moment, MC. And therefore we can figure out as the angle, right? The angle between MZ2, MY2, and MZ1 and the MY1, right? So we can define the alpha B and alpha C, right? Which can be obtained from this arctangent of the MY1 over MZ1. Right? Okay, and then we can plot its shear and bending moment diagram. Okay, I just erase them all. Right, we can plot its shear and bending moment diagram from this shaft, right? The whole shaft, right? So in the beginning, there's a reaction force, right, at the point B, right, and with a constant reaction force, okay, and then there's a shear force from this F1 and remain, and then reach the point C right here, point B right here, and the shear force remain, and then the reaction force at point D, right, in point D. Okay, and then you can plot its moment diagram, okay, from the shear diagram, right? So from the A to B, which is flat, right? And then, of course, for this moment diagram, it will be a linear relation. Okay, similarly for this flat shear, and we get this linear moment. Okay, similarly. Okay, and for this Z direction, the same. We have this shear at point A, okay, and B, and C, and D. Okay, and then we can plot its moment diagram. Okay, it's moment diagram. So we can get the MY1 and MZ1 and the MZ2. Of course, this point will be the MY2. Okay, MY2. Okay. Okay, and the torque produce the torsion and the shearing stress, right? And this moment are produced from the bending, right? And produce the normal stresses and normal stresses. Okay, so that's we already learned previously, and we already learned from the materials mechanics course. Okay, and this axial loading and transverse shear can be ignored. Okay, so we have to consider the axial loading and transverse shear. So the shaft mainly subjected to the torque at the moment. Okay, and the torque produces shear stresses, and the moment produces normal stresses. Okay, and of course the shaft is keep rotating, right? It's keep rotating. Therefore, it has to be the fatigue. Okay, it has to be the fatigue. Okay, it has to be fatigued. Okay, so as what I taught for this fatigue criteria, what's the main two stresses that we have to dissolve first to figure out what's the stresses for this failure, the fatigue failure. Is the sigma A and sigma M, right? Sigma A and sigma M. Of course, in this case, we have the torque applied to the shaft, so we have to take into account the shear, okay, the shear stress, the alternating shear stresses and the mean shear stresses. Okay, and the Kf is the fatigue stress concentration vector. Okay, and the Kfs is the fatigue shear stresses concentration vector. Okay. Okay, so I'm gonna briefly retrospect what we already learned. So the shaft keep rotating, so we have to consider it as a fatigue loading, right? And this shaft is without this axial loading applied, or we can just ignore this axial loading and transverse shear. And the torque will produce the shear stresses, and the force, tangential force, will produce the moment and the normal stresses. Okay. Okay, so sigma A, alternating stress and the mean stresses, alternating shear stresses and the mean shear stresses, right? And what's this bending normal stress? Right here, right? Sigma equals to MC over I, right? C is the distance from the neutral axis to the surface, right? The I is the second moment of inertia, right? So we can get this stresses, bending stresses equal to 32m, the moment divided by d cubed, right? And the shear stress comes from the torque equals to TR over J, right? Torque times the radius over the polar moment, inertia, okay? So we figure out the stress and the normal stress and shear stress, okay? The normal stress and shear stress. So each element on this shaft, we're subjecting to sigma A, tau A, sigma A, tau M, and sigma M. Okay, so finally we get the sigma M equals to the Kf, okay? The fatigue stress concentration vector, okay, times the bending stresses, and the sigma N equals to the Kfs, the fatigue shear stress concentration factor, okay, times the shear stress, okay, times the shear stress. Okay, so we can just combine or integrate those stresses into single normal stress and shear stress. Okay, and we plot this more circle, right? The center equals to the average stresses, okay, and the radius, right? We can figure out what the radius of the Mohr circle is, and then we can figure out what's the principal stresses. And from the engineering definition of this principal stresses, the sigma A has to be greater than sigma 2, has to be greater than sigma 3, right? Therefore, we can define the sigma 1, sigma 2, and sigma 3. Okay, sigma 1, sigma 2, and sigma 3. And if you still remember the von Mises stress, sigma prime, right? So we can plug those sigma 1, 2, 3 in here. Okay, here. So just play with some math, blah, blah, blah. So finally, we get this von Mises stresses, sigma prime, okay, equals to the square root, the sigma square plus 3 tau square. Okay. Okay, and here the sigma, the alternating stress, the von Mises alternating stress, equals to the square root of the sigma A square plus 3 tau A square, and the sigma M prime equals to the square root of the sigma M square plus 3 tau M square. Okay, and the sigma A prime can be used to compare with the endurance limits, and the sigma M prime can be used to compare with the SUT, right, and unit stress and the true fracture strength. Okay, depending on what type of the criteria that you're gonna use. Okay. Okay, so this is what we get from the previous slide here. Okay. So how many of you? Okay. So turn off the mic. So the sigma A here, sigma A prime here. Okay, so we're gonna plot the vectors that we already figured out right here. So and the sigma M prime. Okay, the sigma M prime, we already got it, right? So it's equal to this term. Okay, and then we can rearrange this equation. Okay, we can rearrange this equation to extract this 16 over pi d cube out. Okay, and times a parameter, and we define this term as a parameter A. Okay, and similarly, we can just rearrange and extract pi d 16 over pi d cube, and then we define the parameter B of this term. Okay, B. Therefore, we get two parameters for designing the shaft, right? We got two parameters A and B for designing the shaft. And A and B depends on the moment and the shear stress, the alternating and the mean shear stresses. Okay. Okay, so now let's look into this criteria called the distortion energy, right? I think you guys are already familiar with, and which can be used for the static loading for failure also. Okay, so now we use the distortion energy method, or we define the Goodman criteria. Okay, so the safety vector from this DA Goodman criteria equals to this, right? And we already figured out what is the sigma A prime and what is sigma A prime and what is the sigma M prime are, right? Previously, right here, sigma A prime, sigma M prime, right here. So we can plug these two stresses, right? We can plug these two stresses here. Okay. Okay, therefore, the safety vector from the de-Guman criteria is in terms of the parameters A and B. Okay, A and B. Okay. So, okay, and then we can rearrange to figure what's the diameters. If you still remember, the first key design purpose of a shaft is its diameter, right? It's its diameter, right? So we can just rearrange to figure what is this diameter is. Okay. And before fatigue, check for yielding statics always during first cycle. Okay, during first cycle. Okay, so that's mean if in the first cycle in the static loading, this shaft, this plastic deformation already occurs in the static loading, and we don't have to analyze the fatigue criteria, right? We don't have to analyze the fatigue criteria. Okay, and the safety vector for yielding equals to the yielding strength divided by sigma max prom. Okay, sigma max prom. Okay, sigma max prom. Okay, so how to define the sigma max prom? From the maximum normal stress and maximum shear stress. Okay, maximum normal stress and maximum shear stress. Okay, and we plug these two stresses in, we'll say the maximum volumetric stress. Okay, therefore we can get the sigma max prom. Okay, therefore before fatigue, we have to confirm that the safety vector is okay with ny. Okay, it's ny. Okay. Okay, so let's have this example. This shaft AB, sorry, the bearing A and E are two bearings. So once we mention the bearing, that's mean it's a shaft and keep rotating. Okay, keep rotating. Okay, keep rotating. So here's SO dimensions and the force apply. That's mean we have the gears, somewhere here and somewhere here. Okay, or two gears. Okay, two gears. Okay, and this 200-pound and 600-pound are the tangential force. Okay, the tangential force. And the question is that what's the fatigue factor of safety from the DE Moore criteria? Okay, and the properties of this shaft is the endurance limit and the true fracture strength and ultimate tensile stress. And the stresses increase the MA, TA, MN, TN, KF, and KFS. Okay, and for this materials property, if we already know the SUT equal to 100 KSI, the fracture strength equals to 150 KSI, and its endurance limits equals 24 KSI. So from this DE Moore criteria, whose vector of safety equals to distance DO, safety vectors depends on the parameters A and B. Okay, parameters depends on the safety vector depends on the parameter A and B. Okay, and for this shaft whose torque equals 200 times the diameter, the radius 9-inch, or the 6,000 pound times 3-inch equals to 18,000 pound-inch. Okay. Okay. In this case, the sigma torque, the summation of the torque, if the summation of the torque not equal to 0, that means the shaft whose angular speed is keep accelerating. Okay. Therefore, it's omega not equal to 0, and it is not the case. Okay, that means the shaft is keep the speed, the constant speed, but not acceleration. Okay, but not acceleration. Okay, remember that this what we discussed right now. The rotating speed is a constant, but not acceleration. Okay, so now we can start to analyze the stresses of this shaft, right? So we have the reaction force A and the reaction force at point E, right? And then we can plot its shear diagram. Okay, shear diagram, right? Okay, so from this free body diagram, we can solve the reaction force A, 200 pounds, the reaction force at point E, right, 3,800 pounds, right? And then we start to plot the shear diagram. Okay, the shear diagram. Okay, like this. And then we plot its moment. Okay, its moment diagram. Okay, so once we get its shear and bending moment diagram, which location that we have to specifically consider? We have to consider which location. which location that we have to take into account? At point C, right? Point C. Why? Why? Because there's a fillet, right? At point C. That's mean the stress will be concentrated at the location C. That's mean it will fail or it will fracture at point C. Okay, point C. Okay, so we can figure out what is the moment applied at point C from this shear and bending moment diagram. Is 2400 pound-inch. Okay. Okay, and the mean moment equals to 0. Okay, the mean moment equal to 0. Okay, so if we plot, it will be like this. Okay, so here is the MA. Okay. Okay. Okay, now we can check the table or the chart. Okay, for this stress concentration shape. Okay, we can figure out what is the chart that we can use. Okay, so for the stress concentration vectors KT, KTS, with our shaft here, the capital D here, right here, capital D right here is 5 inch and lowercase d 2.5 inch, and the radius of the fillet is 0.3125 inch, and the ratio between these two diameter, okay, the capital and lowercase d equals to 2, okay, and the radius over the lowercase d equal to 0.125. Okay, therefore, we can from this chart to figure out which curve that we're going to be use, and we can figure out what's the static stress concentration vector is. Okay, okay, so the ratio 2, right? And this ratio is 0.0125. So 0.125 right here. Okay, right here. And the ratio 2, where's the ratio 2? This is ratio 3, and this is the ratio 1.5 and 3. So we got somewhere in between, right? Somewhere in between. Okay, and then we can figure out this the stress concentration vector KT equal to roughly equal to 1.6. Okay, 1.6. Okay, and the KTS shear, okay, shear stress concentration vector. Similarly, the ratio 2, okay, the top curve, okay, and the R over D is 0.125, right? Okay, so we can figure out the KTS is around 1.4. Okay. Okay, so now we already get this KT and the KTS, and the next is the notch sensitivity, right? Because if the final parameter is the KF, right? And the KFS is the fatigue stress concentration vector that can be obtained from the KT and the Q, this notch sensitivity, right? So now we can check the table for the notch sensitivity. Okay, and here we already know the radius of the fillet is 0.3125, right? Somewhere, let me see. Where's the inch? Oh, it's beyond this 0.3, somewhere here. Okay, somewhere here for this radius. Okay, it's a plateau right here. Okay, okay. And what's our ultimate tensile stresses is? Let me check. 100 KSI right here. Okay, right here. Point 3. Oh, it's the we should it should be somewhere here. Okay, so we just roughly evaluate this notch sensitivity roughly right here, right? So the Q vector equals to 0.85, right? Similarly, we can figure out the QS for the shear notch sensitivity equals to 0.88. Okay, similarly, we get this curve. We use this curve, right, and figure out the QS. Okay, so now we have the KT and the KTS, Q and the QS. Okay, and then we can use these two parameters to solve this fatigue stress concentration vector KFS and KF, right? And the KF equals to 1 plus Q times KT minus 1 equals to 1.51, and the KFS equals to 1.352. Okay, now we can determine these parameters A and B, right? We have figured out what is the KF and what is the KFS is, right? And we have this MA and the TM, right? MA 2400 and TM is the 18,000, okay? And the KF is 1.51 and KFS is 1.352, okay? So the parameter A equals to this number and the parameter B equals to this number, okay? So we have the A and B. Now we can get everything like the safety vector, okay? Safety vector, right? We have the A here, oops, one. We have the A value here and B here. Okay, so finally we get the safety vector equals to 5.25. Okay, 5.25. Okay. Okay, so if you guys have any questions, just let me know. Just say something, okay, and turn on your mic, okay, and then turn off your mic. Okay, so for shaft design, so first thing you have to consider the stresses and fatigue, right, and the deflection, okay, deflection, and the speed, okay, the speed, okay, and the speed. And for this deflection, if you still remember, we can use the Cartesian theory for the beam deflection. Okay, and for this critical speed, maybe we're not gonna deeply discuss this issue, but we have to concern its natural frequency or resonance. Okay, so now we just focus on the stresses and fatigue. Okay. Okay, so maybe let me go through this example first. Okay, so there's a shaft OC. Okay, it's OB and BC. Okay, and made by this materials with cold draw, and whose materials property endures limits equal to 40 ksi, the ultimate tensile stress equal to 91 ksi, the KFS and the KF and the KFS already known. Okay, and what's the diameter of the BC? What's the diameter here? What's the diameter here? By using the Gerber and the Goodman, and whose design vector equal 2.5. I'm gonna explain this later. Okay, so here we just say, okay, it's kind of safety vector. Okay, I'll explain this later, but right now just think of it's similar to the vector of safety. Okay. Okay, so we have the force point load apply at location A, and we have the point load apply at location B. Okay, and there's a torque apply between the 0 and the 1,800 pound-inch. Okay. Okay, that's the stresses condition or the force condition applied to this shaft. Okay, so the two key parameters that we have to solve is A and B, right? It's A and B, and the diameter, right? The key vector that we have to solve is diameter of the shaft, right? By using the Gerber and the Gument. Okay, so you can check our last week the slides I already taught last week. Okay. Okay, and in this case, this torque apply with the mean torque equal to 900 and the alternating torque equal to 900 pound-inch. Okay, pound-inch. All right, so it's the mean stress right here, 900, and its alternating torque equal to 900. Okay. Okay, so from this free body diagram, we can use the equilibrium equations to figure out what's the reaction force at C in y direction is, and what's the reaction force at O in y direction. Okay, 200 and 400 pounds. Oops, sorry. 200 and the 400 pounds. Okay, in y direction, and the force reaction force in z direction at point C, right, equals 200. Okay, the same. The reaction force at point O in z direction is 100 pounds. Okay. So there are four reaction forces 1, 2, 3, and 4 in y and z direction. All right. Okay, so now we can plot its shear and bending moment diagram. Right? And we can plot them, even we can plot them in 3D. So we have this shear bending moment diagram in y. It's always like that. In y direction and z direction. Y and z direction, right? Y direction and z direction. Okay. So the reaction at point O is the 400 pounds right here, and remained at point 8, right? There's 600 pounds, right? 600 pounds, and remained, okay, till the point C, which is the 200 pounds, right? 200 pounds. Okay, and similarly, the reaction force in z direction start from this 100 pounds, right? In z direction right here, and remain till the point B, right? Point B, 300 pounds right here, and remain till the point C, 200 pounds. Okay. Okay, and therefore we can use the shear diagram to plot the moment diagram, right? To plot the moment diagram. Okay, again, which location that we have to concern for this fatigue shaft? Which location? Of course, point B, right? Because there's stress concentration. We're concentrated at location B, right? Because there's a geometric change at location B. At location B. Okay. So we have to focus on the location B with its moment, okay, with its moment. Therefore, at point B, whose moment in z direction equals to 2 times 200 equals to 1,200. Okay, and the moment at point B in y direction equals to 6 times 200 equals to 1,200, right? Therefore, the resultant moment B, right, equals to the square root of the mbz square plus the mby square. Okay, so just what I'm saying. So we have this plot, for example, we have the point B here, right? So we have the moment mbz, and I have the moment mby, and then we can calculate the resultant moment mb. Okay, here. Okay. Okay, so from this the mid moment and the alternating moment, the Tm and the Ta, right? From the previously, we get right here. Okay. So we can figure out what is the parameters A and B is. Okay, what is the parameter A and B is? And this Ma equals to 1,697 pound-inch. Okay. Okay, so we can get what's the parameter A and B is, whose value, the value of the parameter A and the value of the parameter B. Okay, A and B, right? And we know that those mean moments and the mean torque and alternating moments and alternating torque, right? And plug those values in the DE Gerber criteria, and the diameter, right, can be figured out. It can be figured out. Okay, so by using the DE Gerber criteria, the DE equal to 1.353. Okay, and if we use the DE Goodman criteria, the diameter of the BC shaft equals to 1.408. Okay, 1.408. The design vector basically is based on the regular code or the company policy. Right? That's mean, okay, so it depends on what's the company or what's the industry that's defined the specific design vector for the specific product or specific components. Okay, so however, for the factor of safety, right, the definition of the safety vector equals to S divided by the sigma max prime, right? So I guess introduce this previously, if you still remember. Oh, it's disappear. Where is it? Okay, but anyway, Okay, so once the design vector is important because we have to consider and the uncertainty of our product, of our design, of our components, like the materials property or the load variation, okay, and what kind of the failure theory that we use or the tolerances and so on. There's many uncertainties for a product. Therefore, we have to define the design vector for the specific product, and they're different. Okay, so the design vector differ from the factor of safety. Okay, so there's one example here. Okay, suppose we have a column with a radius of r and the force P apply. Okay, and the force P apply. Okay, and we have no idea what's the real value. What's the real value is of the P or R. Okay, but we know this stress, as you see, the ultimate compressive stress. Okay, so its variation is plus minus 10%. Okay, and the P, the force applied, whose variation is plus minus 5%, and the radius of this column or this component is plus minus 2%, right? This tolerance comes from the manufacturer. Okay, there must be some tolerances during manufacturing. Okay, and then we can define. Okay, so the stress equals to the force divided by area, right? And the area equal to pi r squared. And we define this stress is the nominal stress. Okay, we define the stress as the nominal stress. And what's the maximum stresses is? That is the high stresses divided by the lowest cross-section area. Okay, that's the maximum stress. Okay, therefore, the maximum stress equal to 1.05 P, 1.05, right? We just pick up the plus 5%, right? And the area, the lowest area is minus 2%, right? Minus 2%. Okay, and then you can calculate the maximum stresses. Okay, maximum stresses. Okay. So there's a ratio between the maximum stresses and the nominal stresses. Right? And for this case, we say the ultimate compressive stress, the minimum of the compressive stress from this plus minus 10% is 90% of the nominal stress, right? Nominal stress. Okay, so therefore we say the worst case scenario is that the maximum stresses equals to the minimum S, the minimum compressive stress. Okay, and then the maximum stress right here, right here, and the minimum stress here. Right, and then we can define the design vector equals to the nominal stress divided by the nominal stress. Okay, nominal stress. Okay, therefore for this design vector, we don't need any what? So for this nominal stress, we don't need any values. No, we don't need any real numbers. Okay, we just need its variation. We can define the design vector. And the main purpose of the design vector is for the company. They're gonna, for example, they're gonna have a new product or new components. They need to evaluate how to define the safety vector, how to define its the tolerance. So they have to figure out what the design vector is before the safety vector. Okay, so there's the other examples. So we have the wrench here, okay, right, with the length of the L and the load applied P. So someone can turn off your mic. No idea what's the proper view. Okay. Okay, so for this nominal stress, I equals to my over I. So y is the distance from the neutral axis, right, to any point. Or c is the distance from the neutral axis to the surface. Okay, so this is the bending stress times the kT, right? This stress concentration vector. Okay, so we can get the nominal stress. Okay, and the minimum stress, the maximum stress, right, will equals to the force, the maximum stress divided by the minimum or the lowest cross-section area, right? So what is the lowest cross-section area? Right here, right? minus 1%, minus 1%. You can use the 0.99t times the 0.99h squared. Okay, and then we can get the maximum stress equals to a ratio times the nominal stress. Okay, and in this case, it's yielding stress with the variation plus minus 5%. Therefore, the minimum yielding stress equals to the 95% of the nominal stress. And for the worst case scenario, the maximum stress equals to the minimum stress. Okay, and the maximum stress right here, maximum stress, and the minimum stress. Okay, and we figure out the ratio between the S nominal divided by the sigma nominal, and the design vector equals to 1.66. Okay, 1.66. Okay. Okay, so the other examples here. So we have the column with a center load. Okay, center load, and the design vector can be evaluated by this equation, right? S divided by sigma. S divided by sigma, and sigma equal to P over A, and whose diameter from the this value that already given, right? We can plug those numbers here, right? And we can get the diameter of this column. It's about 0.4 inch. Okay, so from the spec, the D from the spec, I mean, it's a standard component, okay? And this company provide the standard specs of this components. It's 1/8, 1/4, 3/8, and a half inch. Okay, and for this 0.4 inch, regularly we're gonna pick up the 3/8. However, if we use the 3/8 diameter, we'll make the safety vector that is smaller than the design vector. Okay, and therefore we have to select the diameter equals to the 0.5 inch. Okay, 0.5 inch. Okay, and based on this result, we can plug this number in the safety vector equation, right? So we can, so there's a wrong typos here. This should be safety vector. Okay. Okay, so we can plug the diameter 0.5 inch here. 0.5 inch here. Okay, and we get the safety vector equals to 3.14. 3.14. Okay, so the safety vector is always greater than the design vector. Okay, so for this component, we already know its design vector, and then we find the diameter of this column, and we use this column diameter to calculate its safety vector. Okay, to calculate safety vector. Okay, so this 0.5 inch diameter makes the safety vector is greater than the design vector. Okay. Okay, so I think this course, machine design course, will be ended here. Okay, this is the last course that we're gonna attend. Okay, so next week is our robotic contest, beginning at 1 p.m. Okay, so any one of you would like to join this contest, okay, yeah, just come over at the first floor of the EN building. Okay. Okay, and only the reaction force apply at point D. Okay, at point D.